Okay, so good morning. The plan for this last day of lectures, so this morning and this afternoon, will be to finish the discussion of the ultraviolet limit. Okay, so I remember to you that we were discussing the ultraviolet limit. So I want to finish this discussion, especially show, so today plan is show the second renormalization. Okay, so this is particularity of the not present in d equal 2. Okay, so we will have to cancel, there will be another infinite quantity. So I remember to you what happened in 2 dimension. Okay, in 2 dimension we had the product of distributions, and we introduced at some point, I introduced to you this new objects like the cube with the subtracted and the square with a subtraction, and I claim that these objects are well defined in the limit, while if you don't put the subtraction, they are infinite. Okay, and why I can do it, so this somehow in this context, so in the context of this lecture where we are just discussing somehow how to use these ideas to construct non-trivial Euclidean quantum field theories. Essentially, in this context, the idea is that you don't care what you put as an interaction, as soon as it works. So it's like whatever works. Okay, so why you can do it? Because if it works, I'm fine with that. Okay, there is no. Of course, there are reasons, and you could give a full course on that about this idea of renormalization, what it's really meaning. But at this level, and I think it's, I mean, I tried in the initial part to motivate what we are interested in, and I think it's intellectually correct to say, okay, given what we said, whatever we can do will give us an interacting theory. Okay, and the goal of somehow this line of research is just to construct models for interacting theories, because the difficulty is that there are not so many such models. Okay, so, and in 3 dimensions you have to introduce an additional renormalization, and okay, so then finish. So I want to finish the discussion of a priori estimates, both in finite and then infinite volume. We will see that it will not, essentially, I will not spend much time, because as soon as we did infinite volume, essentially it's just putting together what we did in finite volume and what we did in infinite volume together, that is put a weight and then just check that everything goes through, and you have the infinite volume estimate. And then so this will give tightness for the measures, and we will be able, and existence, if you want, and existence of accumulation points. Okay, so we will have candidates for the infinite volume measure. Okay, and then I want to spend some time to give some property of these accumulation points. So far, we are not, I'm not able to, there is no proof. So far, we don't have proofs of uniqueness within this approach, the Stochastic approach. Okay, so that's an open problem. In general, you cannot expect uniqueness, but essentially uniqueness. So remark, if you want, uniqueness is expected. So that is this accumulation point. Actually, there is only one possible limit when lambda is small enough. Okay, well, if you want. The only thing that count is actually this ratio. Okay, you can rescale the problem and you see that the only quantity which really counts is the ratio lambda over m square, and when this is small enough. Okay, so this is the idea, and it's an open problem to show within this approach that this is the case. Okay, so let me start. So where we were. So I remind to you, so let's see. Let me see what we can say. So let me copy just. Yeah, I was a little puzzled the last lecture because actually I made a mistake. At some point I dropped some term which should not be dropped. And that's why I was a bit puzzled because I didn't, there was something missing and I didn't know where to find it, and because I forgot to write it actually. So let me take this. Let me take the question just to point. Okay, let me just make a small recap of what we were looking at. So I have to find the question first of all, where it is. So yeah, so we had this equation. Okay, so recall our setting. Just briefly recall. Okay, we look at the equation in finite volume. So it was like m equal 1, let's say, and epsilon finite. Okay, so we are on a finite lattice, everything is well defined, and v prime was it was yeah, and v prime was that. What's this? Wait, sorry, I lost. With v prime was given like this, and so we are in 3 dimension, and we take v prime equal to that, and as in 2 dimensions, so we can write an equation of the form. So what we had here, we had like a series of factors. So we will have lambda, and then we will have like, as soon as you renormalize, you have x cube, y cube. Yeah, sorry, not x. So remember, we had y cube, and then we have like 3y squared z, and 3y z squared, and z cube. Okay, and so this is the equation you want to consider, and then we introduce several. We introduce a first transformation, and the first transformation is that we defined this new process. So remember that. Remember what was y cube. Y cube was just the cube of y minus renormalization, which was like this constant 3 lambda y. Sorry, there is no lambda. There is no lambda at this level. Okay, and y square was the square, the renormalized square. Okay, and the combinatorics was like this. And then we define H to be this process. And I don't discuss very much. I mean, in the paper, you will see that actually the question is solved is not this one. Okay, I'm skipping some details under the rug. In particular, if you want to solve this equation, you see, you have, if you want to have good estimates for this equation, somehow you have to guarantee that this object is small, because you see it's like, it will be then a contraction. Okay, if you just multiply H with a small quantity, then you can solve by a fixed point. Okay, solve this equation by a fixed point. Okay, so this equation is not the difficult part. Okay, so now the idea is that you can make this small with a technical trick, and that's not very important. Okay, you have to keep in mind why we wanted to do that. So we wanted to remove some term. Remember what was the point? Okay, we want to do these a priori estimates, and the only information, the a priori estimate will pop out the H1 norm of something. So the only kind of regularity information they give you is regularity of order 1 of the variable you are trying to control. Okay, so everything which needs more than 1 degree of regularity, it's dangerous for us. In particular, this is dangerous because it would require 3/2 degree of regularity, and this is dangerous because it requires a bit more than 1 degree of regularity, okay, to make sense of this product. Okay, so this was the reason we wanted to remove this, and you remove this by just solving this equation and introducing and defined phi to be, so phi to satisfy. So we just now say, okay, Z contains this source term, I want to remove it. And this is very easy, is like what we did when we introduce Y, we just remove H. And when you remove H, then you have a new process. So if you want phi is Z minus H, and then you have a new process which does not contain this and does not contain something here. Okay, so let's write the equation for phi. So let me say which satisfy. What is the equation for phi? Yeah, I'm repeating also because I made a mistake at some point, so I will try to correct it. Okay, so this term will disappear because you essentially exactly removed from here from using this equation. So let me maybe write nicer. So this term disappear from here, and then in this term, you see you added also this term. So somehow here you will have like let me see, maybe -3 lambda y square paraproduct H. Okay, and then you have that. But now remember, we introduced the paraproduct. So somehow here there were 2 paraproducts. So remember that I can decompose this in paraproducts. So let me just decompose it for you. So then we will have 3 terms here because these are the 3 paraproducts. So I'm just writing. So this is the equation, and then you can simplify it because you see, I just copy. You see that these 2 terms goes together, okay? Z minus H give you phi. Okay, so here you will have phi. So this will disappear. And right, good. And here, yeah, that was the mistake I made at some point. So now here you still have Z. So this term will be harmless for us, okay? So that will be good. That's why you want to introduce paraproducts, because they introduce term which does not give you harm, and then you see very clearly the difference between the term which produce somehow some irregularity and the term which is difficult to define, okay? So, but you see, you have Z here, and I want to decompose it, so I decompose it. What is Z? Z is phi plus, so you will have phi, and then you will have H, okay? So you can write something like this. And this was the term I forgot the last time, and this is the origin of part of the renormalization. Remember, renormalization can only appear when you have resonant terms, okay? In the paraproducts are always well defined, so they don't produce an infinity, but a resonant term, somehow you have a resonance, okay? So it's called a resonant term for the reason that somehow you have 2 objects which they could both oscillate at very high frequency, but their product is a very low frequency. And this provoke a problem, okay? Because there is a lot of energy coming from the somehow high oscillations coming back to the low oscillation. So when you are on the low oscillation, you're seeing this lot of energy coming to you, and you're scared, and everything is blowing up. Okay, so resonances are bad. I can show you a movie of a bridge which is torn down by resonance from wind oscillation. Okay, the wind is pushing this. It's like when you go on altalena, I don't remember how to say this in English. Like you push, and if you push at the right frequency, then you build up energy. Okay, this is exactly what happens here. Okay, so somehow these two terms can oscillate a very similar frequency and build like an infinity. So we have to take care of them. And now this a priori could do a similar problem, but in this method, in the method I showed you, we had a trick to somehow convert this term in that term. Okay, so now which satisfy this equation. Now we tested, so this is, let me say, dangerous terms. Okay, so these are the dangerous terms. Let me, dangerous. Okay, then we tested with phi. I think I'm in the right. Yeah, then we tested with phi, and we had, let me see, we got this thing. Okay, so we tested with phi as usual, and then we get the good terms. So I take the good term from here, and then we had also all the bad terms. Okay, please ask question if you feel puzzled. So let me just check that I'm not again saying to you something wrong. No, I think it's fine. It's not the unique way to do. Okay, just I'm proposing. So let's see if we have all the terms. So this term I have. Yeah, this term I want to separate in two parts. So we said I separate the two. Actually, here I have Z, so I think I can put back Z because it's not really. Yeah, you see, I made this mistake here. So I didn't wrote down the right term. So let me write all these terms. So these terms, okay, let me actually be more careful and write it down exactly. The various terms are treated differently. So these two will go together. Then here I have exactly that one, maybe with minus, actually it's 3 over 2 lambda. And I want this one, so these are harmless for me, so I put on the next line. So let me just, so in this way we have somehow a kind of classification of all the possible terms. Okay, so all the terms I put in the last line, somehow they are harmless for me. Okay, just need to be careful that I bring everything with me, but this term is that one. Yeah, I can even remove all the t, everything is computed at a given time. Okay, so that's, we can leave it understood. Yeah, and we have this, I can even put this outside. I don't care very much. So at this level, I think it's more important to just get the feeling of what's going on. So let's hope that the coefficients are correct. And we have something like this. Actually, sorry, let me, yeah, there were a phi around, which I forget. So here I have to put phi again. So this because we were testing with phi. So let me just remove all this. Yeah, and here, of course, there are too many terms because many of them I already wrote down. And you see, I put things in such a way that, I mean, this will have a meaning. All these different contributions, somehow, they must be treated differently. In particular, this contribution, this contribution will be the one generating renormalization. So let maybe make it more prominent. Okay, so this will be treated by renormalization, and this other contribution will be treated as we saw. Okay, so let's see. Okay, so the last one is not a problem. Okay, everything will be, it's well defined in the last one. Okay, remember the regularities we had. So yeah, sorry, let me maybe finish yeah, let me recall the various regularity. Okay, so let me recall the various regularity. So we had this, so I can resume the things here. Okay, we have y1, y2, y3, and the irregularity were like, now let me use k for an arbitrary small positive number, which can be different from line to line. Okay, so this is just to simplify my life, because I don't have then to remember how many powers of k I have. Okay, it's not. So y2 is -1 minus k, and then y3 is -3 over k. But of course, one has to pay attention. What does it mean here? So let me write it in this way, actually. Okay, in the sense, because you recall that somehow this object has to be treated as a space-time distribution. Okay, so a space-time distribution. So this term is a bit, but you can ignore in first instance. Okay, if you don't care, let's not care too much about that. Okay, so let me write in this way. Okay, and H has this regularity. Then these are terms which will appear later on, so let me ignore them for the moment. What we have here, okay, now we have, yeah, okay, these are all the source terms, they appear in this equation. And you see also, because y thinks I'm saying this is dangerous, okay? Y square has regularity -1 minus k, and H has regularity only 1/2. Okay, so this is not well defined. And again, okay, from the Laplacian you can hope to have an H1 norm. So phi has regularity. So phi you can hope as regularity only 1. But actually we will see that actually there is something going on. Okay, you cannot have really phi of regularity 1, because if you think about this, this is an elliptic equation, so you have to see the source term to understand the regularity of phi, and the worst is that one, and y is regularity -1. Remember, the paraproduct does not help you. Okay, so essentially the regularity of this term, so let me write, for example, here, the regularity of this term is 1 minus k, -1 minus k. Okay, so from this you deduce this is not improved. Phi could be C infinity, but the regularity of this is dictated by the term which is taken at high energy. Okay, so the regularity of this is dictated in this way, and then you look at the equation, even if all the other terms they were not here, you get only phi of regularity 1 minus k. Okay, not better. And then we have a problem. Okay, we have a problem here. And actually we have a problem in the, so this cannot be H1, okay? And so when we try to write this estimate, we have a problem, okay? So we did another, so we wrote the estimate, but then we did a transformation, and we did a transformation to get rid of the terms. So we got rid of these two terms. Let me say minus. So first of all, we rewrote. So let me put them on the other side. So we have this term, and then we have plus these two terms. Okay, so this the integral, and then you have plus these two terms actually. So we took this combination, so I could even write on the same side, but okay, here maybe. So we took this combination, what we did. So now this combination is not very good, okay, because we know already that phi is not the right regularity for this term to be, which is ill-defined, in which all the terms are ill-defined in the are again, okay, ill-defined means that I cannot hope to control them separately in the limit. Okay, so that's the idea. Okay, so all these terms, each of them separately, they give me problem. Okay, for various reasons. This term because I cannot hope psi to be essentially because psi has not the right regularity. Okay, this product is not well defined here, and this resonant product is not well defined. Actually, sorry. But what we did is that first we use a commutator lemma. So what is called a commutator lemma, I gave the last time to say that this second term to replace y square. So the commutator lemma replaces essentially this product. So this integral with, remember, okay, so the commutator lemma tells us that you can somehow transpose this operation on the other side. And when you transpose on the other side, it becomes modulo errors, okay? So it becomes essentially the same product. So here you will have like this modulo an error term, and I call this error term like you call it. It's not very important, okay, because this will be nice term. So we don't really care about it, okay. So you will have something like this, maybe with a lambda in front, but we don't care at the moment. And then we introduced a new process. Okay, then we defined. This is the last transformation. Okay, so we defined psi, so that, and I can remove time because nothing depends really on time here. Everything is computed at the same time. Okay, and we introduce phi, so that let's call this quantity, I don't know, A. Okay, so let me define this quantity A like this, and then we have A is really that, and if we introduce phi, then A is given really by, now you can replace A by this, and if I did my computation correctly, this is like completing this square. Okay, so this is like completion of this square, which removes this term. And then when you remove this term, you obtain another square, which is the square of psi, and then the square of this term, which looks like that, maybe with a plus. And then you still have this additional error term, which, sorry, the error term actually is not multiplied. So let me just write, because it depends how you define. So it's just an error term like this. Okay, just a real number. Okay, it's a trilinear operation on three functions and give you a real number, and it's okay when the sum of the regularity is positive, which is the case here. Okay, so maybe you feel lost. so it could be a good point to start to ask questions. So let me resume the point. Okay, so so this was what we did the last time. We still have this red thing. Essentially, we took care of that thing. So far we took care of this. Let's call it. Let's give it a color like I don't know, China. Okay, so we took care of these blue parts. Let's say I also put blue part here. Okay. And then the blue parts are together, and they give this this thing. Okay, so let's put a blue color here. Also. Okay, so we replace the blue parts with these parts. Sure, maybe. Okay, so at this point we have. So I want to summarize because I think we are a bit lost. We have defined, decomposed Z as, so what we have now. Okay, so what if you want, we had this decomposition of actually of let's say of the full solution. Okay, so what we did first, we singled out y1, which is y, and then what we did, we singled out h, and then we singled out this part, and then we singled, and then we wrote that. Okay, so this is just a change of variable. Okay, where it's a bit intricate because I don't want to expand everything I could. Okay, so phi is just you can express as x minus these two, or equivalently as the sum of these two. Okay, it's like it's implicit definition. Okay, but somehow you have different parts. Your solution is decomposed in different parts, and somehow you want to keep track of all of them because they have different properties. Okay, with psi, with these different functions satisfying the a priori equation. I mean the equation, if you want. Okay, so you have now this new equation. So let's see. So the new equation, now I told you this disappear because you have phi. I can even remove the color because now it's not a problem anymore. This disappeared, but generated like a term like this. And actually put me, I will put it, let me think what I want to do here. Yeah, now this term I want to put it in here actually. So now the new situation is that this term has become like something I want to put here. So this is equal to this two, and then we have a lot of other terms, and let me put this term here with the harmless terms. Okay, so this is the new a priori equation. Okay, so you see you have the good guys on the right hand side, and you have the bad guys. The good guys are on the left hand side, and the bad guys are on the left right hand side. Okay, so that's the idea. With the ugly guy in red. Okay, so you have this final shootout between these values. Okay, you have to hope that the good guys win. Okay, so the game is to make the good guys win. But there are the ugly guys. Okay, the ugly guys are these guys because they are not, they contain products between things which are not well defined. Okay, in orange actually. Okay, the terms in orange are still out of control. In particular, they contain products which are not well defined because the regularity do not sum up to positive. Okay, so this is the current situation. Okay, so we have to do, this is the problem now. Okay, we have to understand what happens to the red guys, and we make them harmless, and then I will and yeah, we have to understand what's going on, and actually that's the reason why I put the beta prime there, because we still need a renormalization. And after we did that, we just have to close the argument and show that everything on the right hand side it's smaller than everything in the left hand side. Okay, so let me say section. So this is like the second, or maybe subsection, I don't know, the second renormalization. Okay, so now that's the problem. Okay, maybe before I go there, let me pause a moment. So let me, yeah. And understand and try to understand the meaning of the decomposition. This decomposition. Okay. What we are doing. What is that? So you see, that's somehow that's the point. That's the novelty one has to introduce really to be able to solve this kind of equation. Okay, the idea is that you cannot somehow solve this very singular equation by just looking at solution as an element in a given Banach space. Okay, so the decomposition. So that's the novelty, if you want. So it's a point I would like you to take away from this lecture. Okay, this is the key point of this approach, or these new approaches to singular SPDs, if you want. These are not even singular SPDs, but regularity structures or paracontrol distribution. So we are looking at paracontrol distribution, but in regularity structure, it works in the same way. The message is that we cannot just look at generic functions in a given vector space, like in standard PD theory. Okay, so okay, I don't like in classical. So somehow it's not enough to say, okay, I look at my solution in a given space, in H1, in H2, whatever, in a Holder space. You have to give, you have to be more specific on the structure of the solution. Okay, so this formula, you have to read it in this way. Okay, my solution, the solution to my original problem. Remember, we have this initial problem involving only X, and then we started to introduce change of variables. Okay, and then we expressed our solution as a sum of terms, and these terms have a structure. Okay, in the sense they are more and more regular. So it's like a decomposition, an expansion in the most irregular part, then the second most irregular part, then the third most irregular part, and then what remains. Okay, so it's like an expansion. Okay, but we need to specify the solution as an expansion in terms of different character, okay, maybe even implicit, okay, explicit or implicit terms. Okay, there are some which are explicit, the other are implicit, okay, in terms which are explicit or implicit of different character. In our case, in the okay, so in the paracontrol approach, this involves the regularity or the various terms. Okay? So I can just copy the expression and we have this. Okay, so so what is this a regularity? This is a regularity minus 1/2 minus kappa. Okay, let not me. Yeah, okay. So this is a regularity 1/2 minus kappa. This what is the regularity of this term? Well, this is -1, then you increase of 2 degree of regularity. This is 1 minus kappa. Okay, and this will be in H1 because we will have an a priori estimate in H1. Okay, you see here. Okay, so this is telling you that the process will live in H1 at any given time. Let me remove. Okay. Okay, so you see you have this graduation, and actually it's quite explicit. Okay, for example, one could say that, okay, if I take the little Paley block of X and I subtract the little Paley, so for example, you could say that the little Paley block of X, they go like 2 to the I to the 1/2 minus kappa plus kappa, okay? And then but okay, so this is like 0 order approximation, okay? So let me make a table for that maybe. Yeah, okay, so you will have a situation like this. No, I mean, this guy goes like 2 to the I, okay, this I told you. I'm not precise in the what I mean goes by because I would need to take norms. And you see, sometimes you can evaluate in L infinity norm, but other terms are just integrability, L2 integrability. So I don't want to be very precise at this moment, just to give you the rough idea. In the paper, of course, you find all the details, but I want just to give the idea of if the regularity really matters. Okay, the integrability somehow is orthogonal. The integrability consideration are orthogonal partly. Okay, we will use very rarely Sobolev embeddings, for example. It's not very much used in this context. Yeah, so you see, solution will behave like this. Yeah, but it's not a generic element of that space. Okay, what is telling you this equation is that, okay, if you take the block of the solution and you remove the block of y1, then you get a better estimate. Okay, you get this object, it's smaller. It's actually a regularity -1 minus k. Okay, you see from here. So it's going to 0. This was diverging, but if you subtract this term, then you go to 0. So you see, it's like 0 order Taylor expansion, then you can subtract something to make it smaller. So this is like subtracting the derivative. And then you can continue because you see, you know exactly what you have to subtract to get it even smaller. Now you subtracted that, so you have things which are going to 0 even faster. And if you subtract, and you know actually that you can even subtract something else. Okay, if you subtract, actually add, okay, but that's if you add like 3 lambda over 2 of exactly this object, So you see, you have to find right objects, but when you found the right object, then if you do the right thing, if you subtract the right quantity, then you get even better behavior. Okay. And actually, we will prove later that you have even better than that here. Okay, actually, psi is even better than H1. Okay, it's I think it's 3/2. Okay, if I remember correctly, it has regularity 3/2. But maybe I'm wrong. Let me think. No, I think it should be. Okay, so we have this structure for these terms, okay, which can be interpreted by saying that my solution lives in a very particular subspace of the space of Bezoar function of regularity -1/2. Okay, we could take for example, yeah, integrability, it's not better than, you see, this object has integrability L2, so this object will not be better. Okay, so the regularity is dictated by this, but the integrability is dictated by that if you don't do something. So essentially, you have to use Sobolev spaces, for example. Okay, so it's not a generic Sobolev function, okay? It's some kind of Sobolev function which is random and which you know exactly that if you subtract this function, then it behaves better. And you actually, you know that you can subtract you can construct another random element and subtract it and behave even better, and then even better. And then you stop because you could continue. For example, in regularity structure, there is a systematic way to develop these expansions. Actually, regularity structure are built around this idea that locally in space you can expand and you can describe very well your object. In paracontrol distribution, as you see, the expansion is more like at high energy. Okay, so at high energy, my solution looks like y. And then in first approximation. In second approximation, you have to add a correction. In third approximation, you have to add another correction, but essentially they are ordered. And every correction is somehow unambiguous, okay? Because if you don't exactly subtract this, you don't get that, you don't get improvement in regularity. Okay, so somehow these terms are, if you are able to construct, these are not arbitrary, okay? So what this is maybe what I'm trying to say is that we produce it, I try to motivate it by an arbitrary subtraction, but as soon as you realize what you're doing, you realize that actually there is no other way to produce the same behavior, okay? To filter your solution and write it as a sum of more and more irregular terms, okay? Because somehow this is the best regularity you can get for this term, okay? This term do not live in a better space than that, okay? In particular, okay? So this is not proven everywhere, but somehow I think it's true, and it would be interesting if somebody can make this precise, okay? In particular, the stochastic objects y1, h, and y2 do not have better regularity as those stated. Yeah, they are almost surely not in. So you can say C1, yeah, not in C1 half. You see, if you try to remove K, they don't enter into the respective spaces. Okay, so sorry, it's the opposite. Okay, so if you try to improve, this is like for Brownian motion. Okay, think about all the regularity of Brownian motion. Okay, you can prove that Brownian motion is nowhere all the regular of index 1/2. Okay, if you find a okay. Of course, all their spaces are not tailored for these processes, okay? So that's why you have to allow this small gap, okay? In the scale of all the spaces, there is not a space which describes exactly the oscillation of these processes, okay? Because the older scale is arbitrary. We introduce it because we like it, but has nothing to do with the process. So usually, for example, for Brownian motion, you know exactly what is the modulus of continuity, and it's like 1/2 older, but there is a log correction. And here, more or less, is the same kind of, you can introduce the same kind of spaces, but they're not very useful in the analysis, and they complicate too much the matter, so nobody actually do it. You don't gain anything or knowing exactly the modulus of continuity, because somehow the product of two distribution, you have to have positive regularity. If you have two distribution whose sum of regularity is exactly 0, then somehow the kind of theorem we do, they are not able to distinguish if the situation is good or bad. Okay, you need more refined theories. Okay, so this was a bit an aside note about what is the meaning of this expansion, and that's the idea of all these theories. That is, you have to be more specific. So the space in which you look at the solution is not. You see, it has a very specific structure. In particular, the process. You see here, you have to have something. So this first part is somehow quite elementary in the sense, okay, I'm looking at a solution which is something which is random but fixed, and then something arbitrary. Okay, so you can understand this is like a translation of a Banach space, okay, in a larger Banach space. So it's some kind of a fine set, okay. But then you add more complicated things. So you see, you cannot get away only with this. This we did in 2 dimension. 2 dimension, you get away just translating with a irregular object. But in 3 dimension, you have to be more careful, and you have to be more precise in the description. In particular, you have to factor out this additional contribution, which is not just a translation, okay, because it depends on x. Or phi, remember, it's a function of x. I could write phi as x minus y1 minus h. Okay, yeah, I can put it here. So it's some kind of implicit thing. Okay, and this is what it's called a paracontrolled distribution in some sense. Okay, it's some distribution which can have this description and which can involve a paraproduct. Okay. But I don't want to introduce too much nomenclature. I think the idea it's important, but then how you implement it is not it's not paramount importance. Okay, so let's discuss this second renormalization. Want to do it in the next hour. So we have to care now about this red term. Okay, so let's think about what is going on. We need to understand what is going on with the red term. And I write it again, okay? Which contains not well-defined products. So here now the idea, so let's analyze the first one, okay? Start with that, okay? And use the formula, the definition of H to write. So we rewrite it, okay? So we use the definition of H. So let's remember what is H. I go back. So what was H here? Okay, so let me just copy the definition then so H was something like this. So let me, okay, so it's somehow solution of some equation, and we already, so somehow you can write it. This is like a parabolic equation. So let me introduce like a symbol for like the linear operator. So let me see. So I define L to be like the time derivative plus this object. Okay, so this is like a parabolic operator. And then you have this equation. And then remember that we defined y3 in this way. So when you invert this parabolic operator, you get something like this. Let me do it formally because somehow I don't want to enter. You just to think, you have just to find a solution of the equation. So it looks like this. And so the definition of H was that. Okay, so you just invert this operator, and then you have y3. Recall. Y3 is defined as the solution of the parabolic equation with source y3. Okay. And then what we have, okay, so we have if I took, okay, I just took this, and then I have y2 square, and here you have y2. Okay, just taking the product. Now, this is okay. I'm saying is this okay? This is not okay. Let me think. This is not okay, actually, no? Because, yeah, sorry. Now I'm lost again in this point. Let me check my notes. Yeah, please, if you want to ask question, that's maybe a good moment. I need to check something in my notes. Wanted to illustrate this point, but let me maybe stop a moment. Okay, yeah, so both terms actually, they are not good. Okay, so here we have regularity. Remember, okay, what is the regularity? So with regularity, this is 1/2 minus kappa, okay? Because y3 was minus 3/2. So this product is surely not well defined, and this product is surely not well defined. And then we have somehow here also similar problem, okay? Because you see, you have like y2, if you ignore the phi, which don't play a good important role here, they could be taken constant, and you will still have a problem here. You have y2 multiplied with some elliptic operator applied to y2. Here you have y2 multiplied by some parabolic operator applied to y2. And essentially the problem is the same. That is, y2 has regularity -1, the operator gains 2 degrees of regularity, and here you still have -1. Okay, so this is not good. This is not good, and that is not good. So I start with this term because they don't have phi, so they are easier to look at. So let's look at the first one. Okay, so the first one, okay, for we have that. So now you need to understand. So this object is not well defined according to our estimate. Let me remove this T because it's not very useful to have it around. Then this is, we can show by probabilistic arguments involving weak products that, okay, so the idea now is that you can write this object as a new object, which I call, let me give a name, okay? So I don't know if this notation is meaningful, but okay, you call it a new object plus some constant, let's call it the epsilon, y1. Okay, let me let me do it for and you somehow you have the same situation here. Here the situation is as follows, is that this object, so again, okay, these objects are very explicit, are polynomial of a Gaussian random variable. So you finite polynomial. So essentially you know everything you want. You can compute whatever you want about them. Okay, there are explicit formulas which involve these weak products, but okay, so this is what it's meant, okay, is that whenever you have polynomial of Gaussians, you can do whatever you want because essentially you know everything, okay? It's your problem become a combinatorial problem, okay? There is no much difficulty there. You understand very well what's going on. So here in particular, you can write it as another polynomial that one can define other polynomials y, which I call y to 3 and y, let's call 2. Let me write in this way. Okay, it's not very, just I'm inventing some notation for this guy. Okay, in some paper you see that you use trees, but okay, I don't want to introduce trees. I didn't prepare myself to write trees on TechMark, so let's avoid. So I think it's just, these are just notation, okay? So they are not very consistent because, no, I think they are consistent because somehow this object, it's really, you see, remember what is this object? This object, it's really that, okay? So you see that somehow my notation has some consistency. And here you have, now I have to remember what are the right constants here. So let me, I think you have 3 here and you have 1 here, okay? But where the epsilon is a constant which diverges log with epsilon, okay? So that's the situation, okay? This reminds what we did. This is not much different from what we did in 2 dimension, okay? And in the equal 3 for the products y3 and y2, okay? So exactly, conceptually is the same operation, okay? You have a product of polynomials of a Gaussian which is not well defined, and actually you can prove in the situation we are that somehow you can introduce a new object provided you subtract something. So you have to read it in the other direction. Maybe you can produce a new object which is well defined, okay? So the random fields are converge as epsilon going to 0 to well-defined random fields with regularity okay, such that, okay, we can state the regularities. Okay, so what are the regularities? So y2 will be like in C. Let's say I take a bounded, okay, I don't want to insist too much on the, in time is continuous, and what is the space regularity? You can guess from here that it cannot be better than y1, okay? And actually you can check, okay, this is regularity minus 1/2, this is regularity 1 minus 1, and so somehow the regularity sums in these cases because it's some kind of is related to the homogeneity of certain expressions, and then for this you have minus k. So I have a question. In terms of Feynman graph, do this object correspond to? Yeah, in terms of Feynman graphs, they correspond to the following. Okay, so you have to make. So let's see. In terms of Feynman graphs, one could write. So these are so you have the problem is coming from contractions. Okay, so these two objects are like weak products. Okay, so you have to understand them. So this I wrote like this, but okay, you have to remind that this is like the weak product of y. So this is like y, and I denote the weak product usually like this. Okay, so essentially is the weak product of y square, which you take the product of y cube and you propagate. So let me. So one could write. So let's see if I can do it. So that's maybe. So let's have an intuition of what's going on here. Sorry. So what one could write? Well, you have, for example, phi square. So essentially, you have phi square. So phi square I can represent as, let's say, I represent this as d. So this is phi square, y square. This is like. Okay, and then you have y cube. Okay. Sorry. So you have y square and y cube. Okay. Yeah, I would like to have them. Okay. And so y square is a polynomial of order 2, so it has like 2 legs. Okay. And y cube is a polynomial of order 3, so it has 3 legs. And you don't consider contraction. You don't consider contraction in the same. Okay, so this is yeah. Let me. This is the situation. Okay, you have the product of the two, and you have a propagator. So somehow this object is this. You have to let me. Yeah, I put them too far. Let me try to do that correctly. sorry, let me, so this expression is like this, okay, let's vaguely, okay, because of course we didn't consider the renormalized product, but let's say that vaguely it's like this. Yeah, I don't like, what's going on, text. Okay. So this object is like this, and then you write it as while this object, so now you write the other object. So now this object is the weak product okay, let me, yeah, sorry, let me so yeah, sorry. So what happens to this object? So you can write it in when you decompose it as when you decompose it as so it's a product of two polynomial, and you can decompose it in weak products. Okay, so the idea is that you can, when you decompose it in weak products, you join, like you can join, let me copy, okay, because we have various things. Okay, you will have this, and then you will have let me make it smaller. And you will have like three possibilities. And the first one is that you join just two legs, and of course you have various possibility to do that. That's not, sorry, I don't see. It's not wanting, sorry. No, I want, sorry, I want this. Okay, so you can join two lines, okay, or you can join one. Okay, you can join nothing, or you can join one line. I don't know why it's giving me problem for that, but does not like me today. Or you can join two lines, okay, and of course you can choose, but at the end you will have, yeah, because they are different images, and then every time I have to curve points, it should be like that. Okay, why don't you? It does not like me today. And yeah, you do the same on the other side. Okay, like something like this. Okay, so you get three objects, and these three, so this is in terms of Feynman diagram. So you will get the first one, it's what I wrote, it's y to, okay, I was not precise enough, because somehow, I mean, the first two you call like this. So let me use maybe the language of, so the first one will be like the weak product of y square, and then you have L minus 1, the weak product of y cube, and this is the full weak product, okay? And the first one is this. And the second one is actually where you don't take the full weak product, but somehow you contract one leg here with one leg here. and I don't have a notation for that. So essentially is, let's maybe you contract one leg. I don't have, yeah, let me write in this way. You contract 0 leg. I don't, if you know this language, maybe it's speaking to you. So here I'm meaning I contract 0 leg and then I take the weak product. Here I contract 1 leg and here I contract 2 legs. And then there is nothing more you can do, okay? Because this term does not have more legs. And you see that this object remains with 1 leg. So it behaves like y1. Okay, so here the idea is that this is a constant. So this last object, so this last object, and one has, so this last object is the problem. Okay, what is that? Well, it's somehow you have yeah, I mean you have two legs in one point, so it's like yx, and then you have yz or yy. If you know this, maybe you try to follow. If you don't know, it's not very important because and here you contract 2 legs, no? And then what you have is that this is like the correlation function between 2 legs. Yeah, let me write. This is like the correlation function between 2 legs. So you have something like this time yz. And what happens in 3 dimension? Well, this is like, okay, this is like 3-dimensional. So let's see if I did it correctly. Yeah, these are the 2 correlation functions. Then you have also the propagator for the L minus 1. So you have a third object. So let me call Px minus y. So Px minus y is coming from L minus 1, is the green function for L minus 1, and this is coming from the contraction 2 lines, okay, two contraction line. And what is that? Well, that it's then you can compute this. This is like, now in 3 dimension, the green function behave like 1 over x, and now you see that here there is a problem because this is 1 over x cubed. So this is like yy. Okay, so this is my constant, the epsilon. So okay, you can do actually precisely on the cube. Okay, so you can do, let's do it on the cube, because then you see really that you since the correlation function, so gx, which is like the average of yx with y, let's say y, so gx minus y. So this is like the green function in 3 dimension. Then we already saw how does it look like. It look like the sum over exponential, the sum over exponential I chi x minus y. You know how does it look like. Okay, it's k squared plus m squared, and then you have sum over k in z3. So it's something like this. Okay, and okay, this is actually intersecated. Okay, if we have our minus epsilon minus 1, okay, is something like this. And this goes like, okay, I don't need it actually right now. Okay, whatever. This goes like 1 over x minus y, okay, for small. And P, and the kernel P of, okay, I'm a bit sloppy, but somehow that's the idea. Okay, behave the same, in the same way. Essentially, is because they are 2 very similar objects. Okay, so this kernel behaves like x minus y to the minus 1. Okay, so that's the situation. Okay, so yeah, maybe it was interesting. So the idea is that every time you have like product of Gaussians, somehow every Gaussian is like an object which with certain legs, and when you have the product of two, of course you have a polynomial of order 5, but out of this polynomial of order 5, you can construct what they are called weak products. Okay, so now I'm yeah, usually you put brackets around this guy. So let me, yeah, you put which can compose in orthogonal. So it has a orthogonal decomposition. So I'm not sure if I, let's see if I, yeah, something like this. Okay, so I try to denote that somehow these are weak products. Okay. Yeah, maybe let me remove the. Okay, so something like this, okay? It can be decomposed in 3 orthogonal terms, and I don't care about all them. So somehow the interesting for me is this one, because this one is diverging. The other two are not diverging. Somehow this is not causing a problem, because you see there is no loop, okay? That the last one is diverging, while the other two are well defined. And you see the last one, when it diverges, you can compute it. And so this is like the last one. So let me. So it behaves like this, and you have these two lines, and somehow there is an integral going on, and this integral is diverging as epsilon is going to 0. Okay. And it is exactly diverging with this constant. Okay, this is how you compute the constant, and it's proportional to 1y. Okay, so that's the reason why I subtracted, so modulo this term, I put all the other two terms here, and this object is well defined, and one can prove that it has this regularity. The same for y2, okay, y2 is simpler, okay, you just have y2 and y2, and you see that you have a term where you have this contraction without an external leg. Okay, so for y2 you can do the same. Okay, so you can do the same for so if you want for y2 integrated n minus 1 y2, one can do the same. And actually, since maybe I already have essentially everything, yeah, I should have added maybe this additional line. So let me add it because it's fun to add it. So I needed to add an additional line because, of course, we have L minus 1, which also link, okay, which also link these two guys. I want this, yeah. So let me just add the weekly line. Okay, so this is like L minus 1. Okay, so I can even add. Okay, so this line is L minus 1. And let me. Yeah. Let me add it. Okay, I will complete. But you see, you have these additional lines. So this line, you have 3 lines, and these 3 lines give you 3 power of 1 over x, and this is in 3 dimension, it's a problem. It's logarithmic divergent. Okay, it's small x, which means a large impulse. And so I think it's better if we denote, we point out that we also have this line which connects these two vertices. Yeah, do you have questions about this? Yeah, I know that I don't pretend everybody understand, but maybe if you have familiarity with this with the language of quantum field theory, then you recognize objects you already know, and this allows you to make connection. Okay, and for y2 you can do the same, because y2 is essentially similar to that. So let me just copy, but maybe this. Okay, y2 is only, there is 2 here, there is 2 here, and you have only 2 legs. Okay, so this is y2. So let me adjust. I don't like this. Okay, that's better. And y2 is this, and then you can decompose, of course. So let's decompose it. So this is like, now you have only 2 terms. Okay, when you write the weak product, so you decompose in orthogonal. So this bracket means that they are the orthogonal, like the Gram-Schmidt decomposition of these guys. Okay, and here you have actually only 3. Sorry, again, because somehow you can do the same contractions. And what are the either you don't contract anything, or you contract one leg. Now that I don't want to keep me doing the same thing. You can contract one leg, or you can contract 2 legs. Okay. And you see that when you contract 2 legs, you have the same problem. Okay, you have 3 legs which connect 2 things, and when these 2 things are nearby, then you have a problem. Okay, so this leg is like the correlation function. So let me put the name also. Okay, so this is G. Oh, sorry. Here you have G. Here you have 2 leg with G. Okay, so G. So this is proportional. This is proportional to the integral in the x of x to the cube, which is log epsilon. Okay, in our case, log epsilon. Okay, so this is the but it's a constant here. You see here you don't have more legs. Here you have 4 legs, and then you have 2 legs, but here there are no problems. Okay, here this is proportional to, okay, so here here a cube. Here you see that here you don't have any problem. Okay, that's why I don't subtract it. Okay, you have this is proportional to that, which is finite. Okay, and this is there is no integral, because you don't have any loop. Okay, and then this decomposition give us 3 polynomials. Okay, so we put all these 2 together, and this you call D, and you subtract. So this will give us like what I wrote, like D2. So my notation, this strange notation, just denote these 2 terms together, and then we put away this last term. Okay, where this denote the sum of the first 2 graphs. Okay, so that's the discussion. If you, this is small parenthesis on Feynman graphs, if you understand a bit of this language. For us, it's not important, just we have to care. So the only important information for us is that provided you can define, provided you define them in this way, okay, like this difference. So let me maybe be more explicit. Okay, this object is defined as this minus that. and this object is defined. Let me write on a new line. This is defined as this minus a constant. And I think you see why there is a tree here. Okay, let's discuss this on the Feynman graph. So why there is 3? Because you see that here, I could even write down, okay, here you have 3 choices. Okay, now I would need to do the real combinatorics here. Is this 3 or yeah, the difference, okay, depends what you count. So now here you have yeah, here you have like 3 times 2 choices. Okay, you have to choose one of these 2 legs and then contract to the other leg. And here then you have like other 2 choices, because then you have 2 choices for this last contraction. Okay, so here you have 3 times 2 to the cube, sorry, square. Yeah, do I want to, okay, let me make this smaller. Yeah, just to, so that it's okay. So this is the number of choices you have. Okay. So maybe they are too big for. Okay. And you yeah, a priori you have all this contraction to discuss. So let me add this combinatoric here. So here you have, yeah, here you have, so let's see what happens here, because it depends how I define. Actually, I didn't define, so this is like prop 2. Okay, there is a proportionality constant. So now my constant is this. So let's see here what happens. Let's see here what happens to the combinatorics. Sorry. Maybe it's too small. Yeah, sorry, just now I have to get it right, otherwise I will not be satisfied. Okay, so here, how does it work, the combinatorics? Well, here you see you have to contract 2 legs, and okay, you can choose one of these 2 and one of these 2. Okay, so here you have 2 to the square, and then you don't have choices. Okay, so here you have 2 to the square. So you see that if you define, so let me define these d. So if I define this as d, then you see that somehow with a constant, then you see that in this graph you have 3 times that. Okay, so this is 3 times the same constant. Okay, so you have just to be, this is the reason, because somehow you add more choice in legs. Okay, so this is the reason why here you have 2, but there you have 3. Okay, the way you defined it. Okay, let me go back now to our discussions. Okay, so the only thing we want to know is this. So let me go back. And now let me use this wisdom to analyze, because we still have things to do. Okay, let us go back to this quantity. Okay, we were looking at that, and then we understood that this object causes a problem, and something here causes a problem. But you see here, here it's not right. Okay, so the first step, right to H. Okay, the first step is to use commutator lemmas to show that. So now one has to simplify this expression, because you see, I don't want to have h around because it complicates my life in these computations. Okay, this computation, I ignored this h, okay, just took this product, and I don't want to have it around. And actually you can handle it, you don't need to handle it in this language, because you can handle it before going to that language, because you can write this. Now you have to, so that's the advantage. So, and resonant products. So one has a, so one has something like this. Yeah, let not me, so let me be a bit imprecise. I don't give you the right lemma, but I give you the idea. The spirit is the following, is that whenever you have like a function taking the product of a paraproduct, okay, so then this is essentially, so the paraproduct, usually the object at low energy does not play any role. It's like a constant, okay? So you want to say that this is essentially the paraproduct, the resonant product of these two functions times h, okay? So that's so commutator lemmas roughly say that one can write, okay, one can usually write modulo nice terms, okay? So it's like an approximate algebraic calculus of this object, and you would expect that to have like this, but actually what happens is that this is a better approximation on the right hand side, okay? And similar things happen when, okay, similar statement can be made when there are other linear operation nicely in between. Okay, that is, I can state, so I don't want to give the statement similar what we said, okay, that is the difference of these two guys, it's a trilinear operation which is continuous. Maybe I will comment later on, but for the moment, let me just vaguely say that you can ignore that this object is not exactly equal to that and pretend that it's the same. Okay, and this works also if there are things like this. Okay, and here it will become like this, or even if you have the Laplacian, if you have like this operator, I didn't give a name, but okay, even if you have Laplacian m squared minus Laplacian, then you can do the same. Okay. Okay, so this is the idea. Okay, the idea is that in the paraproduct always play like a spectator role in this compute in the analysis of these objects. Okay, you can ignore it and treat it as a constant, and then it just pops out. Okay, so here, so we had this term inside this product. We have it here. So here we can play this trick. So we can pretend that this object is that object times h plus other terms, which I don't care, okay, because they are not very important at the moment. It's like a multilinear term. It's like something which depend on y square and h. Okay, commutator. So this is the commutator. Of course, it's defined as the difference of the other two, but this is nice. Okay, nice commutator. And now you see that I have the quantity I like. Okay, so this is, I know what to do with that because I already explained to you. So this object now, I want to write it as, so So this is one bad guy, okay? It's diverging, okay? We already saw, but it has a diverging part, it's not all diverging. So what I want to do is that I write with my new object, which I call like this, but of course I have to add this constant, okay? So this object I now rewrite like this, and then time h, and then I have my nice commutator, okay? Therefore, so we can handle the full term. So I can handle this term as, so let's see what's going on. Okay, so this term looks like this. So the first, so I rewrite it, but of course, in the first one, I know already what to do, okay? I have to replace, so this is still a bad guy, okay? Bad guy, ugly guy, sorry. Also, this is ugly in the sense that they are not well defined. I can replace with that one, but I have to pay plus the, okay, plus that, which is diverging, okay, so that's I know. And then on this other side, I did this transformation, so I just write my transformation, okay, here. And I copy the constant just to be precise. Okay, now you see that you separated, okay, so now this object is a sum of nice terms, but you have these two problems, okay, this problem, so let me write, so plus, let me put them on the side because I want to, so I want to separate them from the nice guys. So I will have these nice guys, they don't cause any problem, they are all well defined, but then I have these two things which depend on D, and they are very, okay, so this depend on D, this depend on D, and I can put them, yeah, I made a mistake, sorry. Here I have a tree, of course, okay, that's important at this level now, because you see they are going to be the same. I will have just minus 3 d epsilon, and then you have just y epsilon plus h. Okay, so that's important. Okay, that's why I'm careful about these numbers, okay, because they go back. Okay, so this object, you see it had a problem, and actually I know now what is the problem. Okay, the problem is that it's diverging and proportional to that quantity. And we see precisely how this term diverges as epsilon is going to 0, okay, due to the presence of the epsilon. Okay, so let me go back where we were. So I just go back a lot because I want to see where we were. Yeah. So we were here, actually. We're trying to handle this product, okay? Because this product appeared here, okay? And we handled it. And now you start to see why I keep around this object, because somehow I hope that this object is killing. Okay, I can choose it. I can choose beta prime to kill all this d epsilon popping up. Okay, but I still have to care about this first term. So let's look at that. Let's look at that now. Okay, I handled that up. That's finished. And let me look at this term now. Okay, I don't care for the moment. I don't care the constants around. Okay, so now my task is, now our task is to handle the other dangerous term, which was that one. Okay, let me give a name at this because I will write many times, and in the paper we call it q minus 1. Okay, with q is just the elliptic operator. Okay. Okay, But now somehow we know already. So this term, we can decompose it with paraproducts. So now the strategy is similar, but of course, and some commutator lemma. So the idea is that now you want to rewrite this. The first thing you say is that, okay, this term contains two kinds of contribution. There is this actually, yeah, you can prove, yeah, let me, so essentially this term is equal to that, okay? The two paraproducts are 0. And one can define the paraproduct so that is true, okay? So when you take an integral of a product, only the resonant term counts, okay? Sorry. The resonant term counts in integrals. Because somehow the other two paraproducts, they oscillate and they cancel in the integral, okay? So let's call it, we call it this B, and then I write like this, good. And now one has to use the same the ideas, okay? So here you have even two paraproducts, not only one, but the idea is the same. That is, you can rewrite this. I can rewrite this as an integral. So let me say, I can rewrite this as an integral where the paraproducts are outside. So I can treat them as constants, okay? So at the end, you will have a product like this, and then you will have phi square, because of course the phi go out, but they don't go out of the integral. And then there is some commutator. Let's call it C prime of, and the commutator depend on everything, okay? So it depends on that, and I write always as multilinear functional, okay? Because another consideration is important, okay? So this is a commutator. Again, okay, it's a nice commutator. Which can be ignored, okay? So the idea is that everything is well defined. This term was not well defined, so I could write in red. And yeah, let me maybe write in red, so that we track the terms which are still dangerous for us, okay? So let me write it in red. Yeah, let me maybe try to do that like this so that I don't. So this was dangerous. What I did here? Okay, this is still dangerous. This is still dangerous. So red is dangerous. Okay, so these terms are not well defined because the regularity do not match. But when I'm here, that's okay. So you see the paraproduct highlighted in red. So the paraproduct the commutator, it's fine. And now here you see that you see something like above, okay? The same consideration as above apply to the explicit polynomial. And one defines, this is not different from, okay? So I need just to define a slightly different object, but let me use this parenthesis, okay? So this is like this minus, and now you check that you have to subtract exactly the same quantity, for example, okay? Sorry, and with the same constant as above, okay? This is very similar, okay? It is very similar to what we did for Y2 So the other one was with the other, just the linear operator was different, but essentially the same consideration applies, okay? And in particular, the divergence is the same, okay? Divergent part is the same. That's important, okay, very important. Okay, so at the end of the day, we finished. Now there is no red part anymore, okay? B is the sum of what? Well, I have this, I have a commutator. Of B gives. Okay, so here I have to replace with my nice guy plus the epsilon. And then I have that, okay? So of course there is still some danger from this part, so maybe let me, but the dangerous part now, it's very easy, okay? It's a constant times something. So let me write like this, or let me keep the constant inside. Maybe let me write in red because we understand that it's dangerous. Okay, this is still diverging, but now I isolated the divergence in a very easy term. Okay, I think we are in a good point because somehow we finished this and I can put all the pieces together. So let me go back. Yeah, it's not very red. This is orange. So let me make it red. That's better. Okay, red, it's better. Okay, now it's red. Okay, so now I go back to this term and I put all I learned together. So let me just rewrite it. Okay, so I rewrite it. So this term was like this. Now we have constants outside. Then I have, so I'm looking at the first one. So this is like this q minus 1. So let me write q minus 1. It's maybe easier to see. So I have the constant. Then I learned that this part was, wait a moment, I have too many, there is no phi here actually. Yeah, here I made a bit of mistake. The phi is only, let me see where, sorry. I made a mistake. There is no phi in front of everything. I already put the phi here, but somehow the phi is here and here. And then the other terms. Okay, yeah, so that's now okay. Sorry for that. Okay. Yeah, so here it does not change anything. Here it's okay, and here just to rewrite that. Okay, now it's fine. So I have this, and then I have this integral. That's fine. And the commutator. We don't care about the constant for these terms, but let's put them again. What are important is now the constant for this term. So let me put it here because this is still red. So I have this. So this is the first part. So now I have this part with minus 3 over lambda. Let's see what's going on here. Here I have the integral again. Then I have phi, and then I rewrote y square resonant product of H. Okay, this is like this. So let's go back. What was our rewriting? So this term looks like that now. Okay. Why I have this lambda? Yeah, because there were a lambda inside H. Okay, so there is this additional lambda. This is important to track. I hope I didn't make any mistake. So now this object will become all this guy. So let's be patient a moment and just and then I have this part. So So here, what's going on? So these guys are okay. This is okay. The only dangerous, I want to highlight only the dangerous part, which is the last step, because it's the one I care for the moment. So I put away here, and I leave it alone on that line. And okay, that's not an error. So let me write it in red. So this term is now, yeah, maybe with the constant and all, because it's not clear how to separate things. Okay, so these are now the dangerous terms. Okay, and I can put even them together. So let me put them together, because then we will see. Okay, now I have a small problem. Yeah, I think I made a mistake at some point, and here there should be a lambda square, because somehow this lambda was coming from the fact that, let's go back a moment and just check that I'm right. Why I claim you have lambda square? It's because you see here you have this paraproduct comes with 3 lambda over 2. Okay, so when you put 2 of them, you have of course lambda square. And I'm sorry for the mistake, but you see, this has to be like this, otherwise things do not work at the end. So let me go back, and I have a lambda square there, and then lambda square. No, here it was fine because somehow it's taken care there. I think I had lambda square here and only, yeah, from this term. Okay, now you see that I have lambda square 9 over 4, so both of them are the same. And here you have d epsilon phi square, and now I have to, yeah, the signs are not correct, but okay, at the end of the day, this should just give you a phi here, okay, like this. And I'm worried that my signs are not correct, so maybe I will have to check the sign, but let's say that I have something like this. We'll have to check again the sign because they don't match. Maybe I made a mistake, but it's not very important for the moment. So the point is that we have his. Maybe check the sign. Let me put a remark for myself here. Okay, but at the end of the day is this. And now you see the magic, okay? You see, this is exactly what you have here, okay? And now the remarkable fact is that we can choose beta prime to be, now one has to find the right constant, maybe 9 over 2 lambda square. So the fact that there is lambda square is important, the epsilon. And okay, maybe minus, this I'm not sure. Okay, so check the sign in order to cancel the divergence coming from the epsilon. Okay, so that's the key point, okay? This means by choosing a property beta, we can change, yeah, we can remove all the developments coming from ill-defined products of irregular Gaussian polynomials. Okay, so this is possible because this model is super renormalized, or in the or also called subcritical. Okay, in the sense that somehow every time somehow the linear part dominates the estimate in the part of the equation, dominates the regular term in small scale. Okay, so somehow it's more, or said otherwise, the nonlinear irregular terms can be treated as a perturbation of the linear part. Okay, so this is all phenomena that somehow it's related to that. I should say that in this approach, or in general, in this approach where you decompose things, is not very easy to understand. You see, I've done very precise computation, and at the end I can check that everything works, but somehow it's not easy to get an a priori theorem for that. This theorem exists for regularity structures. And actually in regularity structure, one can prove in a systematic way that a certain class of models, which are called subcritical or supernormalizable, they can essentially, you can control them analytically, and moreover, every singularity that it appears, if the noise is Gaussian, you have to use the fact that the noise as a law you know, and it's Gaussian, with a certain covariance. So you have to use all the characteristics of the model, but essentially you can prove that every singularity it will appear, you can cancel by an appropriate choice of parameter in the model. Okay, so that's somehow what happens here. Okay, so let's finish here for now. Takeaway from this morning is that by introducing new objects and by choosing beta appropriately, we can cancel out the singularity. Okay, now in the equation, we have only objects which has a limit as epsilon. Okay, let me make it the point. Okay, we are at a point where in our a priori estimate, we do not have any more bad term, ugly term, or the products are well defined with the available regularity, and the only step remaining is to check that we can close the a priori estimate. Yeah, that is what I mean, estimate every term in the left-hand side with the good terms in the right-hand side. This is very badly said, but that's theory. Okay, so this we'll do in the afternoon. This will be okay. I will do this afternoon, and then we will study some properties of the measure. Okay, so